Hello students, this is Mr. Allen, and today we are going to move into a new portion of Chapter 8. I do realize that this is a long chapter, so I'm kind of breaking it into two parts. Sections 1 through 6, we're dealing with infinite series, and now starting in section 7, 8, 8, 9, 8, 10, we're moving into Taylor polynomials and Maclaurin series and Taylor series. So anyways, so we're going to kind of move in a new direction based on what we've been working on so far in this chapter. So our main objective in this section is to find a polynomial approximation for the elementary functions and compare those with those elementary functions. We'd like to be able to find Taylor and Maclaurin polynomials, approximations for elementary functions, and we'd also like to use something called the remainder of a Taylor polynomial. So to find a polynomial function p that approximates another function f, begin by choosing the number c in the domain of f for which f and p have the same value. So p of c would equal f of c. In other words, the graph of f and the function that's going to approximate f intersect at the same point. The approximating polynomial is said to be expanded about c or centered at c. So this c value is very important, and we'll need to worry about that because that's what's going to differentiate a Maclaurin and a Taylor polynomial. Geometrically, the requirement that p of c equals f of c means that the graph of p passes through the point c of f of c. Of course, there are many polynomials whose graph pass through c f of c. To find the polynomials whose graph resembles the graph of f near that point, one way to do this is to impose additional requirements that the slope of the polynomial of the function must be the same as the slope of the graph of f at that point c f of c. In other words, we want to force f prime of c to equal f prime of c. I said that the wrong way. P prime of c must equal f prime of c. With these two requirements, you can obtain a simple linear approximation of f, as shown in this figure. So here we can see the function f, which is the curve, the darker curve, and then you can see the linear approximation p. Now here's the key idea. Close to the value of c, that linear approximation is very accurate. In fact, we did that back in Calc AB. We used linear approximations to approximate the values of functions. Now let's look at an example. A first-degree polynomial that approximates the function e to the x. So for the function f of x equals e to the x, find the first-degree polynomial for that function. So p sub 1, the 1 means it's going to be the first-degree polynomial, is simply going to be a sub 0, which is going to be just a number, a numeric value like 3 or whatever, plus, and then a linear term, a sub 1 x. So some other constant a sub 1 times x. In other words, this is kind of like mx plus b, whose value and slope agree with the slope and the value of f at x equals 0. So what we need to do first is figure out what is f of 0. Well, f of 0 means that we're taking e to the 0, and e to the 0 is 1. So f of 0 is 1. We also need to look at the derivative or the slope of the tangent line at 0. So f prime is also coincidentally e to the 0, which is also 1. So what I'm saying here is the value of the function at 0 is 1, and the slope of the tangent line there is also 1. Because p sub 1 of x is equal to a sub 0 plus a sub 1 of x, we can use these initial conditions to figure that out. In other words, we want p of 1 of 0 to equal f of 0, and we would conclude that a of 0 equals 1. Again, if you were to, let me go back to that last piece. If you plugged a 0 in for x, that a sub 1x would be just 0, and therefore a sub 0 has to be 1. Moreover, because p sub 1 prime is equal to a sub 1, we can use the initial condition that p sub 1 prime of 0 equals f prime of 0. We can conclude that a of 1 is also 1. Therefore, p sub 1 of x is equal to 1 plus x. Now look at our figure, our diagram. We can see the curve f of x equals e to the x. We can see that we have come up with a function p sub 1 of x. It's linear, and it is going to approximate that curve as long as we're close to x equaling 0. And in fact, if you look carefully, right very close around 0, it's actually a very good approximation. Now, as we move away from x equaling 0, obviously it's not as good. The polynomial approximation for f of x equals e to the x is expanded about c equals 0. So in this case, c is 0. For expansions about an arbitrary value of c, it is convenient to write the polynomial in this form. So now look what we have here. We've got p sub n, that means the nth polynomial. We're going to do a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c squared, etc. In this form, repeated differentiation process, the first derivative of our polynomial that approximates it is going to be a sub 1 plus 2 times a sub 2 quantity x minus 2 plus 3 a sub 3 quantity x minus c squared, etc. If we do the second derivative, we will get the following. So now that 2a sub 2 is the leading coefficient, or the leading term. The coefficient of the linear term now is 2 times 3 times a sub 3 because we're doing repeated differentiation. And so in general, the nth derivative of the p approximating function is going to be n times n minus 1 times n minus 2 times 2 times 1 times a sub n. Letting x equal c, we would obtain the following. P sub n of c is equal to a sub 0. P sub n of the first derivative is going to be a sub 1. P sub n, the second derivative, is going to be 2 times a sub 2 on through P sub n to the nth derivative of c is going to be n factorial a sub n. And because the value of f and its nth derivative must agree with values of P sub n, its first derivatives at x equals c will be as follows. F of c will equal a sub 0. F prime of c will equal a sub 1. F double prime of c divided by 2 factorial would be a sub 2, etc. With these coefficients, you can obtain the following definition of a Taylor polynomial, named after a mathematician by the name of Brooke Taylor, and a Maclaurin polynomial. By the way, the difference between a Taylor and a Maclaurin is Maclaurin always has a center of 0. You may want to add that to your notes. And here are our definitions. So you'll see. In fact, I'm going to start with the one on the bottom. The one on the bottom for the nth Maclaurin polynomial for the function f is p sub n of x is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 divided by 2 factorial times x squared all the way through the nth derivative of the function at 0 divided by n factorial times x to the n. That is a Maclaurin polynomial for f, and you will notice that the c value here is 0. The more general representation is the Taylor polynomial. In fact, I usually will just refer to them as Taylor polynomials in general. The only difference between the two is the Taylor polynomial will allow us to deal with different centers besides just 0. So you'll notice that instead of it being x squared in the Maclaurin, in the Taylor polynomial, it will be x minus c quantity squared. So let's see an example of finding a Maclaurin polynomial for f of x equals e to the x. So now we're doing the exact same thing we did earlier. Since it's a Maclaurin polynomial, we know that c is going to be 0 in this example. And we're going to play the same game that we played earlier. We're going to do the first derivative. First of all, e of 0 is 0, so a sub 1 is 0. So that's why that leading term in that polynomial is 1. We did that earlier. Then when we do the first derivative of e to the x, we get e to the x again. When we plug in 0, you're going to get 1. So the second term is going to be 1x, or just x. Now when I do the next derivative is going to be x squared. Now I've got to account for the fact that I'm doing this repeated differentiation. So notice that in this case, I'm actually dividing by 2 factorial. Now let me go back to that previous slide and show you what we're talking about here. Look at the Maclaurin polynomial definition on the bottom, and you will see that the third term is f double prime of 0 divided by 2 factorial x squared. So you've got to make sure you put that 2 factorial on the bottom, and just to remind you, 2 factorial is just 2, so that'd be 1/2 x squared. Sorry about the bell. All the way through the nth term, which is going to be 1 over n factorial times x to the n. All right, so let's go ahead and talk about the remainder of a Taylor polynomial. So we're to our third objective here. An approximation technique is of little use or value if we don't know how accurate it is. To measure the accuracy of an approximating of a function using f of x by a Taylor polynomial or Maclaurin polynomial, you can use the concept of a remainder. We did this when we talked about the accuracy of some of our infinite sums. So f of x is the actual function, so that would give us the exact value. If I plugged in some number for f of x into the function, that gives me the exact value. The Taylor or Maclaurin polynomial is going to give us an approximate value, which is going to be off some in most cases. And so therefore, we got to add this little bit of remainder. So notice that the notation is that f of x is equal to p sub n of x plus r sub n of x. And hopefully that makes sense because r sub n, r stands for remainder. And then the p sub n, that's our polynomial, whether it's Taylor or Maclaurin. So if we just adjust that equation, the remainder function of this equation is going to be just f of x minus the Taylor polynomial of the nth term. The absolute value of the remainder is called the error, or the error associated with the approximation. So if it's off by 0.2, the error is 0.2. If it's off by negative 0.2, the error is 0.2, the absolute value. The next theorem gives us a general procedure for estimating the remainder associated with the Taylor polynomial. This is important. This important theorem is called the Taylor's theorem, and the remainder gives the theorem is called the Lagrange form of the remainder. So this is going to be, for those of you that are shooting for 4s and 5s on the AP exam, this is something you definitely want to star. So here's what Taylor's theorem says. If a function f is differentiable through n plus 1 terms in the interval I containing c, then for each x in that interval, there exists a z between x and c such that the function will be equal to the Taylor polynomial up through the nth term of that Taylor polynomial plus the remainder function for that particular polynomial or for that function, where r sub n, this is the key part, is equal to the n plus 1 derivative of f of x at z divided by n plus 1 factorial times that factor of x minus 1 to the n plus 1. Now, guys, I'm realizing that some of you right now might be scratching your head thinking, whoa, this is getting quickly over my head. You're definitely going to have to practice these to get used to them, but it will make sense. And this is just an extension of what we've been doing or earlier in this presentation. Let's look at our final example here. The third Maclaurin polynomial for sine x is given by, so now we're talking about a new function. We're not talking about e to the x, we're talking about sine of x. And I'm telling you that the p sub 3, that is the n equal 3 Maclaurin polynomial for sine, turns out to be x minus x to the third over 3 factorial. Now, you would, if you want, you could take the time to go ahead and verify that, but you will find out that that is indeed the Maclaurin polynomial. It says use Taylor's theorem to approximate the sine of 0.1 by p sub 3.1 and determine the accuracy of the approximation. So, guys, I'm telling you, this Maclaurin polynomial is an approximator for the sine function. It is not going to give us the exact value of the sine function. We want to know what is that approximate value and how far off is it. All right, so we're going to use Taylor's theorem. And Taylor's theorem tells us that sine of x is equal to x minus x to the third over 3 factorial plus the remainder sub 3 of f of x. So that's going to be x minus x to the third over 3 factorial plus the fourth derivative of sine evaluated at z over 4 factorial x to the fourth, where z is between 0 and 0.1. Remember, our c value here is 0, and we want to calculate the sine of 0.1. So now what we're going to do is we're just going to substitute the 0.1 into our Maclaurin polynomial. When we work that out, we get 0.1 minus 0.000167. So that gives us a value of 0.09933. So that is the approximate value for sine of 0.1. Because the fourth derivative of sine is sine, we just need to figure out what sine of z is. It follows that the error, which is the absolute value of r sub 3 of 0.1, has to be bounded by the following. It has to be greater than 0. And in this case, we literally define it as sine z over 4 factorial times 0.4 to the 4. And it also has to be less than 0.001 over 4 factorial. The reason is sine in general is going to be at worst 1. And this is a subtle thing. That 0.001 is not 0.001 times, because we don't know what sine is. We're approximating it, but we know that sine oscillates between -1 and 1. So the worst it could be is 1. So that's good news. That means we can bound this thing. And it turns out that 0.001 over 4 factorial is 0.00004. This implies that, now remember, our original value was 0.099833. So that's the lower end of sine of 0.1. Now, if I add our error to this, that's going to give us the upper bound. In other words, the very bottom line is the most important line here. Sine of 0.1 has to be greater than 0.099833. Simultaneously, it has to be strictly less than 0.099837. So what I would encourage you to do, if you're kind of shaking your head at this, I'm looking for my calculator, here it is take your calculator right now and just go ahead, make sure you're in radians. I'll do the same. And just calculate the sine of 0.1. And then compare that to the answers that we've got here. And you will indeed see. Now, keep in mind, the calculator isn't even giving you the exact value. It's having to approximate it as well. And so that should take us to the end of our presentation. Have a good day.